Thanks. I'm Jason Laska. I lead the engineering team at Clara Labs. The work I'll present today is joint work with Joey Carmelo. Pictured there, he has actually done a lot of the work that I'll present here. So Clara Labs builds a product that helps recruiters schedule meetings and interviews. The product interacts in natural language over email. Scheduling is a critical task that recruiters must do as part of their job. It can be repetitive and interruptive, and sometimes mentally taxing. Our product supports recruiters' scheduling needs through each part of the recruiting funnel. So for instance, if a recruiter is doing a qualification screen, our product will find a time with the candidate over natural language in email. So you can see on the right here, the recruiter depicted by this woman with the blonde hair is copying Clara. Clara goes and negotiates a time with the candidate with the green box around him, and they get a time on the calendar. As a recruiter, you can also ask Clara to find a time for hiring managers to call candidates. So in this case, the recruiter also initiates with Clara, but we set up a time between two other people, one of them being the candidate, one being the hiring manager. And Clara can also intelligently search for back-to-back sets of meeting times for on-site interview panels. So you can see the candidate on the left needs to come on-site to your company, and we need to allocate a large block of time for him. And then solve this traveling salesman-like problem to get a sequence of interviewers ready to interview this person. When we book an event, we can attach your favorite conference tool, such as Zoom or Google Meet, and we're working on CoderPad as well. And we can push the times back to your applicant tracking system so that you can keep your source of truth there where you're already working if you're a recruiter. This is actually a really hard problem. For example, we get messages like this. This is not super uncommon. I'll give you a minute to read it and think about how you might handle it. We'll revisit. And so to solve this problem, we employ a human-in-the-loop system, which combines the consistency of software and the intuition of human intelligence. And we've done a lot of meetings with a platform like this, and it's enabled our customers to be very productive. So in this talk, what I'd like to talk about first is how our human-in-the-loop system works. This will be a dive into kind of a systems level view of our tasking system. Next, I'd like to talk about a specific type of task and problem that we work on. In this case, temporal normalization for attendee availability. This is the problem setup. And then we'll talk a bit about designing annotations to solve that problem. You can think of this talk as kind of zooming in deeper and deeper as we go along. All right, so human-in-the-loop at Clara Labs. At a high level, our system works as follows. An email comes in. That email goes into some kind of natural language understanding component depicted by this gray box. Once we've processed the email, we can think of this box as answering the question, what's new about the emails. Once we've processed the email, it goes into an automation system. The automation combines the annotations or the predictions that we got with state that we already have about this active piece of work, as well as product logic that helps us determine what to do next. And then that also yields some kind of output that says these are the emails we want to send, these are the times we want to select, et cetera. That goes to some kind of very fast review and QA process, also done by a person, and then if they commit it, then it goes out to the customer. So you'll notice there are humans in two parts of the system. In the natural language understanding part, they are used to develop training data sets, and they provide a feedback loop to kind of our machine learning algorithms. And on the QA side, they actually are a feedback loop to what are we missing from our product, what doesn't make sense in our product. And so you kind of get these two feedback loops running. One goes to the product team and one goes to the machine learning team. In this talk, I want to focus on the gray box, the natural language understanding component. So let's dive in a little bit deeper there and just see what's under the hood. So under the hood, we have this tasking graph. So in this picture, each task type is denoted by a different color. And as you can see, some tasks are dependent on the completion of previous tasks, which leads us to this graph-like structure. Some tasks can be done in parallel, while other ones need to wait for other ones to complete. when we design these tasks, we design them to be relatively stateless, low cost, and fast to complete by people. The graph is actually a bit dynamic, which I'll dive into in a moment. Each task type can be done by multiple annotators. Those annotators may be people. They may also be your machine learning algorithm or your machine learning algorithm plus some glue code. Again, we perform multiple annotations per task type, and then we aggregate those results to produce a final value, which will then be used later on or be used in the next task. So to give a concrete example of what this looks like, one can imagine that this pink box is the final value that we got for a signature task that, say, splits body text from signature text, which will then be used in the next availability task that only cares about the body text. So this is a very simple dependency. And then that availability task may be performed by a number of people. It may also get a prediction associated with it. And we do some kind of smart aggregation to produce a final result, which is what we think the true annotation or underlying annotation should have been. And this all happens in a real time as emails are coming into our system. So multiple annotators can be pretty expensive, and we aim to reduce human annotations where we can. So we leverage machine learning when it's accurate enough. So a lot of people like to think of these systems as being really binary, like either a machine does it or a person does it. Our system doesn't quite work that way. Firstly, as you saw before, a machine could do one task type and a person or a set of people could do a different task type. But in this case, we may also look at a machine's accuracy and say, let's just add one more person. So we have an assignment algorithm that selects people from a pool that are online. And that person may do the task, and we will assess what we think the new accuracy is or confidence of this result. And if that does not cross the threshold, we'll assign another worker. The way we do this is we actually learn the workers' accuracies on every part of every task that they do weekly. We use an expectation maximization algorithm that looks at all of the work that they've done together and assesses both their scores and refined estimates of these aggregates after the fact. That's done offline. Further, the assignment algorithm takes into account a number of things that part of them just impact the product. Because it has a real-time nature to it. But also, if somebody is online and we think that they are a very high performing at a certain variable that we have very low confidence in, we may select them. So we'll do this until we exceed some threshold, or we do it for a max number of annotators. If we know in advance that this task is super hard or that the bot is like totally failing on it, maybe we'll just start with 3 annotators to get them out in parallel. And this framework also enables us to run multiple tasks or multiple machine learning algorithms in parallel and kind of A/B test them, dark launch new models, and see how they're performing in the field. So that's our, and then one last thing about the tasking system. Since we get these accuracies of the annotators every week, we actually have a whole operation around how to make those annotators more accurate, which leads to more accurate training data. And we show them for every single part of every task what their performance is and give them a tool where they can go back and practice and learn how to perform better on that specific part of the task. So on the left here, I'm showing a real screenshot from just one task type, which has many things in it. And on the left is someone who's higher performing. You can see less red. Someone on the right is lower performing. And that lower performing person can go and try and improve their score. And we can use this for maintaining and working with the workforce. Great. So that's our tasking framework at a bird's eye view. Now I want to dive into one problem that we really care a lot about, which is temporal normalization for attendee availability. So what is temporal normalization? Temporal normalization is the idea of taking date and time text and maybe some context and normalizing it to a timestamp on the calendar. So in the first example here, you have speaking on Friday, September 7th at 11 a.m. And if we know the year that it was written in and the time zone, we can put it on the calendar. We can define a very specific timestamp, resolve it. We may have less information, such as the talk is on Friday at 11, and maybe we're given some date context, like that statement was written on September 5th. In that case, we may be able to infer what the true timestamp was, although now there's some probability associated with it. And then, of course, there's anaphoric context as well. So maybe the talk was mentioned earlier somewhere, and we know the exact date of the talk, and now we see that the talk on Friday corresponds to that, and so we can find the timestamp. So this is the idea of temporal normalization. I want to browse a few common cases that we encounter in scheduling all the time. So one really common case for us is recurrences. So we actually care a lot about not just mapping to a specific timestamp, but mapping to a recurring set of days or time intervals on days. We think of this as kind of like a cross product between date and time, as opposed to a big range of start date time to end date time. We actually, in our system, we resolve everything to some kind of recurrence rule tuple, which is a subset of the iCalendar spec. So this includes a string that says which days, if given, a start date, an end date, a start time, and an end time. And the actual recurrences are kind of like a cross product between the dates and the times. Also, I'll give an example of what these R rules look like for these other cases. So we're interested in intervals. So time intervals are just times on a day. We're interested in date intervals, which may give us a range of days. The days may be specified. The times on those days may not be specified. And so we have to use product logic to infer what makes sense with those things. We care about open-ended intervals before 10 a.m., after Tuesday, and these also define different kinds of rules. Very common in our case are co-references. So in the top example here, I have a sentence with a token Thursday or Friday that defines 2 days, and then in another sentence later on, 2 different times are defined. And so we have multiple pieces of text referring to a single point on the calendar. In this case, they may be shared across multiple references to the calendar. There's also demonstrative pronouns. Either of those sound good is very common, as well as chain relations. So that Monday may reference something earlier in the thread of the conversation. And then we also have functions. These are, once you've resolved some of the information, you may be asked to take the beginning of a month or find the middle of the week. Another common one is to add duration to a time. And then in our case, we also have something unusual, which is kind of like an intent associated with the calendar reference. So someone may be traveling or unavailable or available. We need to know that information in order to do something with that calendar recurrence that's been presented to us. We also get a lot of irrelevant information, such as good morning, have a great Friday, that we also need to be able to filter out if we're doing something automatically. There's actually a number of other complex intents of this kind. Another common one is Friday's good, but how about 3 p.m. instead? These are really challenging problems. So the example I showed earlier, this is how we would like to resolve it. We'd like to say that the true availability was between 9:10 and 11 a.m. And this is by applying 40 minutes to 8:30, which we know was unavailable, knowing that after 11 a.m. was unavailable, and that just generally the morning is good. So this is a pretty tricky example, and this is how we would think of it in our framework. Great, so that's the problem. How do we develop tasks for people to do this in semi-real time and that we can also predict back into? So previously I showed the tasking system, and this is a little bit more detail about the task itself. So one way you can annotate this kind of data is to just do direct calendar entry. So Friday, September 7th at 11 a.m., put it on a calendar. There's some really good advantages to this. It's pretty fast, and there's a lot of UI for calendaring already out there. It's non-expert friendly, so you don't have to learn a new tool, and the data is directly usable in automation downstream. Some of the problems with it are that the people doing these annotations have to apply the product logic in the annotation. So if somebody says that they're free on Monday, the person annotating this may apply business hours when they do the annotation. They may also inconsistently interpret the text. And those two things make it pretty hard to measure the accuracy of the people doing this. And then, of course, makes it difficult to build a training data set out of it. I put a star next to that because there's a really cool technique for using this kind of data that I'll highlight. On the other side of the spectrum, you could do kind of what a machine learning person would like to do, which is just tag every little piece of the time expression. So Friday is a day name, September is a month name, 7 is a day of the month, and you take all of these tags and the data under those tags, you put that into a logic block with some reference time, and you spit out a timestamp. And this is how most folks approach the problem. The kind of model that you train is like some kind of tagger that tags the time components. This has some good pros to it. You don't have to do a lot of thinking. This is really just tagging things based on what they appear to be. There's usually an objective ground truth. There's always some ambiguity, but a lot of these cases are pretty doable. Most of the product logic that you care about ends up in that logic block, which is software, so you can change it later without changing your data set, and it's directly usable to train some kind of tagger. The problem is that it's pretty slow. So even if you're pre-filling a lot of this data with some kind of active learning technique, it can be pretty challenging. The logic block itself may be complex to build, and that block itself may be inaccurate. This we find is quite a challenge with recurrences as well. If you're just doing timestamps, this is a lot easier. When you're starting to look at more broad categories of date times, this becomes more tricky. So one more method that's out there that I'd just like to point out is this great idea called parsing time, learning to interpret time expressions. There's an awesome set of papers out there. And what they propose is that the training data is actually data on the calendar. They're timestamps. They train a probabilistic context-free grammar model to predict the tags. Those tags go back into your logic block and spit out another timestamp. And the idea there is that in your objective function where you're computing the difference, you're measuring the error on the annotation and the predicted calendar timestamp annotation. And this is a really cool technique. We're exploring more ways to do this. We find it quite challenging in our case because timestamps, again, a lot of this depends on that logic block, and timestamps are a lot easier to do in this case, and there's a lot less search space. Once you start looking at recurrences, expressions become more vague, and it's harder to train a good model for it. There's some pros and cons. The pros and cons of this are a mix. It's non-expert friendly, and it's fast to enter data, but then you're encoding product logic into your data set, and you get these differing interpretations. Great, so I've kind of showed this spectrum. There's a spectrum of slow, high precision, expert annotations, and then fast, low precision, non-expert annotations, and we live somewhere in the middle, so I'll talk a little bit about our system. So in our system, workers don't select time parts, they select the whole time expressions when they need to make a selection. It goes into a simplified schema that we've defined, a logic block, and then we spit out recurrence rules. So recurrence rules are the output of our system. Some of the principles we've used when designing this is we try to avoid any kind of manual text entry when possible. We always favor tagging. There's a lot more UI elements you can do there. We also only show contextually valid data entry tools. So if someone tells us something is a time versus an interval, we will only give them the tools needed to make that time selection. And then we aim to keep it keyboard-only compatible so that people who want to just work on the keyboard and never use a mouse should be able to. We also restrict what we annotate. So we mostly only annotate date cross time style recurrences. We want workers to minimize their assumptions about missing data and really annotate what the meaning of the text is to their best ability. So not infer anything about the text and not leave anything out. When they select text, they can give it an intent. We will then color the text with that intent. So if someone's available, they'll see green. If they're unavailable, they'll see red, etc. This makes it easy to kind of read and spot check what you have selected and make sure it makes sense in the context. Our tool also enables those kinds of co-reference annotations. So multiple tokens can be joined together, and we can be told these two pieces of text belong to the same point on the calendar. And after the data about that text is filled out, workers are able to see a preview of what they've entered, and that preview should closely match the meaning of the text that they've selected. For dates, our ontology is pretty simple. You can have no date. You can have a fully specified date, which is pretty rare, or just some kind of enumerated type, such as a day name or today or tomorrow. If an interval is specified, any interval can come with specific days, just like a recurrence rule. So those are optional. And then to specify an interval, they can give it to us in a form of a week of or a month of, etc. The next n days, the next n weeks, or in very rare cases, a very fully specified date-to-date expression. And then, of course, we allow tagging of demonstrative pronouns, which are those dates, intervals, and times. So that's dates. Again, remember, we only support date cross time, so we annotate dates and times separately. For times, there can be no time. There can be any of the time parts, hour, minute, or meridian. There's a few kinds of intervals. There's fully specified time to times, and then there's some product-defined enumerated types, such as morning, lunch. Morning can mean a variety of things, but in the context of the product, you want to define that. So those things we ask are tagged as opposed to inferred or guessed. And then there's time zone lookup. For either date or time, you can apply a function to it. We have a limited number of functions: before, after, take the beginning, take the end, or the midpoint. And those can be applied to the dates or the times. And so this very restricted ontology actually gives us quite a bit of expressibility of the kinds of things we end up seeing in the scheduling context. So this enables us to do annotations that look like this. The gray box there is the preview that the workers see. I've omitted the tool itself that they use, as that's an ongoing thing that we're always working on. But you can see that several pieces of text can be collected and combined. In this case, that day and mountain time are both used in both expressions, but refer to different points in time on the calendar. This is also a real aggregate from human annotators with no machine learning assist. So they can be quite very short amount of text can contain a ton of information. And so we see that there's all kinds of things going on here. So we found that without any of the ML assistance, these tasks they take less than 30 seconds on average to do. We're getting hundreds of thousands of annotations a month now that have all this really rich information around the temporal expressions for detecting them, co-reference information about them, and normalizing them to our unique ontology. And we're driving our automation today off of this data. So in addition to the things we predict, anything that is annotated in this way, all of the times that we suggest, not all, the majority of times that we suggest or confirm in our system before QA are generated with this data as an input. There's other inputs such as the customer's calendar and other preferences. The top, these are just examples of some of the things we're able to do now that we have this data. So the top is just an NER example where we can now recognize these date expressions, not using regexes, but actually using a trained NER model. And the bottom is that kind of availability intent. So you can see that actually in this particular example, the data point that we got the annotation that we got was not very accurate. But the model actually did quite well on this. It even picked up the demonstrative pronoun there. So what have we learned? So our tasking framework that I talked about in the first part enables high-quality data collection, and there's a dynamic graph based on how many workers we need and based on scoring of those workers that lets us efficiently, in both time and cost, get annotations in real time. And then in terms of annotation design, aim to apply product logic and software. Consider redesigning your ontology for the non-expert annotator to get better training data as opposed to just what your ML algorithm will need. Maybe put some more work into the algorithm itself so that the annotations are simpler. Always tailor your annotations to the problem. And one last thing to call out is I've only explored one task type here, but we have many task types, and each task type may call for a completely different design or UI depending on what kind of data you're trying to annotate. These pictures are me and Joey at the Train AI conference, so thanks to Joey. That's it. I'll take questions from here.